name is Karsten.
I'm Lydia.
And I'm Brian.
And we are mechanical engineering students at the University of Alaska Fairbanks.
This semester we worked with the Geophysical Institute and Don Hampton.
And we were tasked to make a Aurora film scanner.
In the 1950s and 60s, there were a series of all-sky imagery cameras across the Northern Hemisphere. They were capturing Aurora film to be studied, and in the Geophysical Institute here at the University of Alaska Fairbanks, there are still 2,000 spools of this film in storage. Don Hampton at the Geophysical Institute wants to get these digitized and open source because they contain historic and scientific information. It is all 35mm film, and each frame contains an image of the all-sky camera. It would cost $600,000 to digitize this professionally, so we were tasked to digitize it cheaper.
That is a lot of money. How do we do this? We need a machine that'll handle our film at our price. Now, our first problem is taking a full spool and putting it on an empty one. The radius is going to change while we do this, so how do we ensure everything moves at a constant speed? We must also consider the shift between each frame has to be less than 2 human hairs. The film will be the limiting factor. In other words, individual crystals of the film need to be seen in the final scanned image. A crucial part to achieve this will be the light source. We want the brightness of every pixel to be even and have high contrast. The scanner must tackle all these problems with high accuracy for our scientifically significant film.
And here's how we did it. Here we are, we've got our spools on. We're going to be coming from our outtake spool down around this guide. This is just serving as a guide roller. We're going to come up into our nice solid guide that controls where the film is in reference to the camera. This also holds our diffusion and our lights to make sure we have a nice, clear, good image coming down. We're then coming down to our driver motor. This one is a very precise radius that is using the sprocket teeth. It moves 40 steps to ensure that we move exactly 1 frame per movement in front of the camera. We're going to go nice down around there and fold back up into our intake reel. And then as our intake reel spins, it'll suck up the film and we can go our nice, easy 1 film at a time. We're going to power the whole system. We have lights, we have camera, we have the action. Here's our calibration. So what this is doing is we have these stops at the top and bottom, so it's able to check its distance between the two and center themselves. It knows what the distance is supposed to be, so we can measure the amount of steps it takes to find the radius of each spool. Now we have it rolling film by film. We can see how much slower this one over here, because the radius is so large, is spinning compared to where we are over here, the uptake that's super small. This was the difficult factor. This one is just going to spin the exact same amount every time because we're the 40 steps calibrated to this radius.
To wrap up, we achieved our goals of having a low-cost film scanner. Our final cost without the camera was $600, which is 1/1000th of the price to send it out professionally. This film scanner is now at the University of Alaska Fairbanks, and it can be used on all of the Aurora film and any other scientific and historic film here or in other universities across the country.